All right, sounds great. Well, let's go ahead and get to this. I've already kind of solicited some help from the people that kind of joined early about which problems that you guys are interested in seeing. And it looks like 12 and 13 sort of came to the forefront a little bit. It seemed like more people wanted to see 13, but it seems like it might make more sense if I talk just very briefly about number 12 first. So I'm going to move to number 12 here, and we'll read through this quickly and start to make some determinations. I got to move some stuff out of the way here. All right, it says, and I'm assuming everybody can see the problem on your screens. If something by some chance prohibits you from doing that, please let me know in the chat. But it says you've got a revolving light that's located a half a mile from a straight shoreline. It's turning in a clockwise direction with a constant angular velocity. If the beam of light is moving at 2 miles per hour along the shoreline, what is the angular velocity of the light at the time when the beam is a mile from the perpendicular? A mile from the perpendicular. A lot of that, syntax, a lot of the language can be a little bit confusing. So one thing is for certain that we know is that the light is located right about here, let's say. So we're going to call this the angle measure, and we'll use theta for that. And basically this light shines a beam, and basically it sort of illuminates the shore, whatever it's doing. It's like looking for like swimmers swimming in the dark. I don't know, whatever it's doing. And we're only concerned with really what's kind of happening through the light shining along this portion of the shore. And we are concerned with finding the angular velocity, which I'm going to go ahead and I'm going to put that down as my find. Just to kind of show you all, it doesn't matter the order that you write your find and your given and so forth, but finding the angular velocity is just the same as finding the rate of change of the angle measure. And I think just that piece of advice alone might help more than half of you solve the rest of the problem without me saying anything else. But if you think about theta, that's like the angular position. So it seems like it would only make sense that the derivative of theta would be the angular velocity. So we're going to go with d theta dt as our find. Okay, well, when specifically are we going to be finding d theta dt? So if we continue to read, we see that it says that we want to find this angular velocity at the time when the beam is 1 mile from the perpendicular. That's what's very confusing. What they're basically saying is they have this beam at the split second shining right along this sort of hypotenuse, and this is the 1 mile. That's what they meant by the 1 mile from the perpendicular, this being obviously the perpendicular. Now I have to be careful. I don't want to label that as 1. I want to label this with some variable. I'm going to call it A. One thing that you guys are going to have to understand with this session is that my variable choice may not be the same as your variable choice if you've already started the problem. So you might have to make those adjustments. But I want this A to equal 1 at some stage. Okay? Now, you'll notice that the 0.5 is already in the picture, which is nice. That's a constant. And it says that the beam of light is moving at 2 miles per minute along the shoreline. So that would be the rate at which this distance along the shore is changing. That's the given dA dt in this problem. And I'm going to ask you all a question. You're more than welcome to chime in the chat. dA dt would technically be equivalent to, what do you guys think? Would it be equal to 2? It says the beam of light is moving at 2 miles per hour or 2 miles per minute along the shoreline. But would it be positive 2 or negative 2 though? See, I want to say it's going to be negative 2. And the thinking there is that this A distance is getting smaller. Now, we're going to kind of revisit that idea here at the end of the problem, and we'll kind of double check and make sure, did we get the right sign for the dA dt? Because the rate of change of this angle, since this thing is kind of moving this way, and it's to the right of the perpendicular, I'm thinking that dA dt should be a negative value. So we're going to find out if that's the case here in a second. Perhaps this will lead to that. So that is tricky, though. I know it is turning clockwise. So does that mean it would be positive? It's like the rate of change of the angle. Well, actually, I want to take that back. I don't think it is turning clockwise. Correct? Oh, it does say it's turning clockwise. Oh, good job, you guys. So we're not going this way. You guys are paying attention. So we're going around this direction. So A is not getting smaller. A is indeed getting bigger. Very good, you guys. So all it would take is that different word. If I said counterclockwise, then we have a dAdt that's -2 then. All right, good. So we're going to go with dAdt to be +2. Now we have to think about what our equation is going to be. Obviously, there's information and discussion in this problem about the angle measure, so it sounds like it would be a SOHCAHTOA. Looking at the problem, no doubt we would like to use that if at all possible. Obviously, A is going to have to come into the picture, so it looks like to me that this is going to use tangent, isn't it? So we're going to take the tangent of theta and let that be A over 0.5. That's going to cause for a fairly easy derivative. I'll switch colors here to break the monotony. So the derivative of tangent is secant squared theta. Tack on d theta dt. And then when we take the derivative of the right side, we would have 1 over 0.5 times dA dt. And now all we have to do is just plug in the stuff that we know to find the stuff that we're trying to find. So if we let the dA dt be 2 divided by 0.5, is that 4? I believe that's 4, right? 2 divided by 1/2. So you'd have 4 on the right side. Now we have to figure out what is the secant of this angle. But see, now we have this locked in, right? We have this thing sort of frozen in time to where we said that this value is 0.5. This value would be 1. Again, this is our theta. Secant, we know, is equivalent to 1 over cosine. So if we just find the cosine and flip it upside down, we're good to go. The only problem with that, the cosine involves knowing that side. And I told you that I will try to throw as many perfect little 30, 60, 90s at you as I can. That doesn't, or I'm sorry, perfect Pythagorean triples as I could. That's not always going to be the case. This problem would very likely potentially be a calculator question, but I want to show you how you could still answer this without a calculator. In fact, there's very few problems in the entire homework that I really did feel the need to use a calculator on. But that doesn't mean that they wouldn't be calculator problems potentially. So for this particular case, we would take 0.5 squared plus 1 squared and set that equal to c squared, right? Using the Pythagorean theorem. So we end up with, well, 0.5 squared might be a little bit tricky to work with as a decimal per se. So if you change this to a fraction, 1/2 squared is 1/4 plus 1 would be your c squared. So c squared is going to be, what is that, 5/4? And by the time we solve this for c, we would take the square root of both sides, at which point we could end up taking the actual square root of the bottom 4, which is 2, and then have the square root of 5 on top. Basically, and this is a very, very unknown, somewhat not real popular triangular sort of arrangement, but if you ever have a right triangle where the long leg is twice as big as the small leg, then the hypotenuse is always the square root of 5 times the short leg. It's kind of a neat little trick with the Pythagorean theorem, but in no curriculum in geometry that I know of is that really taught. That's something that you wouldn't have to know in the SAT or ACT, but it's kind of cool. A long leg that's twice as big as the short leg in a right triangle, that means the hypotenuse would be the square root of 5 times the short leg. So we know our c value, so if we take the cosine, which would be 1/2 over the hypotenuse, square root of 5 over 2, and simplify that. That's 1 over the square root of 5. That's the cosine of this angle. But to turn that into secant, we would have to reciprocate it, thus giving us the square root of 5, and then squaring that gives us a 5. So your final answer for this is indeed 4/5. The label would be radians per minute, 4/5 radians per minute. And to kind of avoid any other confusion, it is a positive answer because you guys nailed it. This thing is moving clockwise. And in this particular orientation with this triangle, that means that this would be an angle increase. Okay, so looking at number 13 then, I don't know if we need to do the problem from start to finish. If you feel like we need to do that, I will. I will promise you this. I'll at least tell you what the answer is so that if you guys want to keep going, that's fine. Oops, there's a message in the chat. What is the angular velocity of the light at the time? I think my label is correct. I think I do want radians. Does everybody agree with that? So it is an angle measure, so it would be radians per minute. Okay, it is in radians per minute. Double check me though. I don't mind you guys questioning because I can definitely make mistakes. You guys know that better than anybody. All right, so if you look at 13, it's a very similar scenario. The only difference is that the specific moment that we're going to try to like take the derivative and do all that is not so much when, I'm going to kind of redraw the picture here. It's not so much when this distance right here is 1. It's when this angle is something very specific. And in one case, it's 45, and in the other case, it's 30. I believe you still have the 1/2 mile over here. So it turns out that you're going to do the very, very same thing. This problem will require you to do both part A and part B because it asks for what is the difference in the speed that the light moves along the shoreline. If we call this A, distance A, then what we're trying to find now is dA dt. All right, hopefully that sort of makes sense. You basically in this problem, the big difference is that you know, or you're going to have information about the dA dt, you just don't know you know information about the d theta dt, you don't know what the dA dt is. So the thing that kids overlook in problem 13 is that you have to use number 12's answer. So yes, when you take your derivative and you have that d theta dt that pops up into the picture, we're going to go ahead and use that 4/5. All right? Because it says the same revolving light located 0.5 miles from the shoreline now turns with this constant angular velocity. This constant angular velocity. I'm double checking something here. I'm making sure that that's what I've got in my notes. No, 1 rotation per minute. What does 1 rotation per minute mean? I'm not so sure we want this to be 4/5 because it isn't tied to that problem. So if we have 1 rotation, that would be, well, how many degrees is that? That would be 360 degrees or 2 pi, right? And if it takes 1 minute to do that, and if I'm dealing with a measurement of minutes, then I could call this 2 pi over 1, I suppose. That would be my radians per minute. So what that would allow me to do then is to use the rest of the information in this problem and find dA dt that would be in terms of something per minute. Since this is in terms of minutes, I know that my final answer for dA dt would be in terms of per minute. The only difference is my measurement for the distance of A's change would have to be in miles. So your label is definitely going to be in miles per minute. But I stand corrected. You do not want to use 4/5. My problem was I didn't read the question. Okay, so you do not want me to read the answer to you because the answer that I have in my book is wrong. So let's go ahead and take a look at this and see if this is going to be correct. So let me kind of tidy this up a little bit. So we're going to find dAdt, and we're going to actually find it in two specific instances. We're going to find it when theta is 45 degrees, and again, when theta is at 30 degrees. So what are we given? I know that normally we write the given above the find, but we're going to change that here. So what are we given? Well, we're given the 0.5 again. We know that. Well, we're given this very, very powerful piece of information that we just talked about, and that's the fact that the rate of change of the angle is going to be one rotation translated into radians would be 2 pi, and we're going to do that in 1 minute's time. Okay, so basically d theta dt is 2 pi. Okay, anytime you see language like this in an angular change problem, you're just going to use 2 pi. One rotation means 2 pi. All right, it looks like we're going to probably use, would you guys agree, the tangent relationship again? There's a little bit of a lag going on with this computer I'm using, so that's why it looks like I write like a first grader here all of a sudden. I would say that I write like Mr. Meunier, but that would just be rude if I said that I wrote like Mr. Meunier. Yep, he heard me. He heard me. He heard me. All right. Actually, Mr. Meunier's writing looks much better than mine right now. So we're going to, he said no. So we're going to go ahead and take this derivative, and we get secant squared theta d theta dt. And we're going to get 1 over 0.5 dA dt. Maybe I just need to slow down a little bit. So next up, well, dA dt is what we're trying to find. D theta dt is our 2 pi. Secant squared of theta, we're going to have to find, and it's going to be, luckily, a little easier, I think, to find these things. You got two different scenarios. The first scenario is when this angle is at 45 degrees. So if you think about this, if this is a 45-degree angle, how many degrees is this angle? I know you're thinking 45. You don't even have to tell me. So that would make a 0.5, right? So that would make the cosine, let's see, if this is 0.5, and then that would make this side 0.5 times the square root of 2. Yes, all I'm doing is really avoiding the Pythagorean theorem and just using the 45-45-90 relationship. I decided to change 0.5 to 1/2 though. Okay, so in the first part, A at 45 degrees, your cosine is going to be 0.5 divided by 0.5 over radical 2. So that would make the secant equivalent to 0.5 radical 2 over 0.5, right? That should be a theta there. So we'd have the square root of 2 as secant of theta. So what does that make secant squared? Obviously, 2. Okay? For 30 degrees, what you would need to do is use a 30-60-90 relationship. This obviously has to be our short side, right? So to get from the long leg to the short leg, we would divide by the square root of 3. So this is a little trickier. You have to take 1/2 and divide by root 3, which would look something like this. So that would be your short leg there. And then to get your hypotenuse, you would then take this guy and double it which would turn it into 1 over the square root of 3. Hopefully that makes sense. It's just using the 30, 60, 90 triangles a little bit. Okay. Once from here, you're at this point, you would just take, for your secant for part B, you would have to find the secant of theta, which again is hypotenuse over adjacent. So that's kind of tricky. What is 1 over the square root of 3 divided by a half? Well, that's 1 over the square root of 3 times 2. So you'd have this. And then when you square the secant, oh my gosh, this pen is so sluggish, you would get 4/3. So hopefully, as sloppy as this is starting to look, unfortunately, you can see then that you would have to plug in the 2 for all of this stuff to do part A. And of course, don't forget that d theta dt was 2 pi. And then you would plug in 4/3 in for secant squared of theta, along with your 2 pi for this. And then you'll have 2 different dA dt's that you would indeed subtract from one another. Does it matter the difference that you subtract them? Somebody asked. Yeah, it does. I think what we're looking for here, though, to be honest, is really like the positive difference between them. The problem didn't really state specifically. We're just wanting to know how different they are from each other. So we really don't really care so much about positiveness or negativeness. So. All right, hopefully that helps a little bit with the angular velocity problems. To be honest, I think a lot of you that were watching this were like, oh, wait a minute, this isn't really any different than from the rate of change of angle problem that we did in class with the space shuttle. It's not. I'm using a little bit different terminology. And then I know in problem 13, the phrase rotation per minute was a little bit different, but we just know to use 2 pi from that. If you want the honest truth, I don't think you have a problem that's coming up on the test that will talk about angular velocity. And the reason is because my physics people will all probably agree with me that you do a little bit of those in physics class. So I know that they're kind of taken care of in curriculum that we have somewhere here at Avon. So, all right. I had a question in the chat. Yep, the test is Thursday. The test is not tomorrow. The test is going to be on Thursday, which is for only periods 2 and 6, and then the test would be Friday if you're in period 5. Okay. The only question I have with this is the 45 degrees with the shoreline. Oh, that's what this angle here would be, Ahmed, right? 45-degree angle with the shoreline. I know it's almost like this is a problem that really needs a much richer picture than what you were given in problem 12. So, okay. One other question about, I guess, on the 270B quiz or the unit test, I don't think you're going to see angular velocities on either one. You guys have already seen the quiz, or hopefully we'll be seeing it very soon, right? Because you want to have it done by early tomorrow morning. But that particular quiz, I don't think has an angle change problem on it at all, if I'm not mistaken, right? I think everything is. I think you have I know you have a square. I know you have a cone. I don't think that there's an angle change. So. I saw some requests to look at number 11. In fact, I think I had a couple of people through either straight up chats or private messages here that wanted 11. One thing, well, it's not like a big deal that you guys know this. I won't look at them. There's a way, like if you chat with one another that says, hey, Mr. Rickard's a dumbass, he's stupid. What's he? I could see those, but I'm not going to look at them. But sometimes kids are like, oh my gosh, they're mortified to know that you can like chat with each other. Yeah, if you can bash me, that's fine. Have fun with it. I won't look at them. All right, number 11. We got a tightrope walker. Oh, this ought to be fun. So moving along a tightrope at a rate of 3 feet per second at an altitude of 100 feet. Find the change in the angle of elevation of a searchlight when the walker is 200 feet horizontally from the light and walking away from the light. Again, I got to move some stuff around. I know you can't really tell, but there's tons and tons of things all in the way, and I can't see my picture anymore. So here we go. So yeah, this is kind of a new problem, by the way. I have not, this is a first for this question. I think it has not appeared on a homework ever. So hey, lucky you guys. So let me, yeah, the other way, spam the chat there. So what we're going to do is start listing out maybe our given. Already have a halfway decent picture. Tightrope walker moving along a tightrope at a rate of 3. Okay, so this person's walking like this direction, right? And it won't let me write it. Wonderful. Okay. But you know, that part of the picture really doesn't have anything to do with our seemingly it looks like a right triangle. So I want you to realize that that's the same thing as this particular line right here. Hopefully you guys can kind of see my pen cursor moving along. So that is what that 3 is. Now, that being the case, here's what we have to discuss. If we call this A, would that dA dt be a positive 3 or a negative 3? Well, it's moving away from sort of the subject of the problem, which is the searchlight. And I think that's the way that you could probably best answer it. So if we're moving along this direction, I think we're going to say that this is going to be a positive dA dt, right? That's what I have in my solution. Okay, so if dA dt is going to be 3, we know that the altitude of this walker is 100, so this is going to be locked in. And searchlight's kind of transfixed on him. Find the change in the angle of elevation of the searchlight. This would be that angle of elevation that we'll call theta. And we want to do this when the walker is 200 feet horizontally from the light, and then the walking away from the light helps us decide that that really was meant to be positive. So what are we trying to find? We are going to find d theta dt, and we are going to find d theta dt specifically when A is 200, which means it looks like we've got pretty much all of the information that we need, except, of course, for an equation. So our equation would be, well, we look again at the picture. We have this constant over here, which is vitally important. We have this particular value here, which is seemingly going to be useful, right? So again, we're looking at a tangent. And in the real world, the tangent function is probably going to be used much more often than probably the sine or the cosine, just because it's that hypotenuse that sometimes is the difficult thing to make measurements for. So this would be an A. Now I want to throw something at you. This is totally up to you. But whenever I see something like this, I kind of think, oh, that's not fun. The derivative of 100 over A is a little bit trickier than the derivative of A over 100. So what you would have to do with that is call this 100 to the times A to the negative 1, which is no big deal. We do that all the time. But another trick, if you want to use this, is you could flip both sides. Okay, now what was the whole benefit of doing that? Well, the derivative on the right side's a little bit easier, and the derivative on that's a tangent, guys, sorry, cotangent. And then the derivative of the left side is really no more difficult except for the fact that you need a negative sign. That's the only difference. So if we do take the derivative of cotangent, we would end up with negative cosecant squared, right? D theta dt. And I notice if I write really slowly, the pen picks up a little bit better. All right, I'm going to double check some things too because any video that's playing could slow us down. By the way, we got 44 people in the chat watching the video. That's awesome, guys. Good job. So what's going to happen is then d theta d, the dAdt is what we know. We know that that's going to be equal to 3. So this is 3 over 100. Okay. Hold on a second. Okay. Just making sure people are muted. All right. And then over here on the left side, the cosecant squared, looks like we're going to have to look at a specific moment. That moment is when A is equal to 200. So rather than redraw the picture, I'm just going to kind of let A be 200. And then this is going to kind of push you a little bit in terms of asking you if you remember something that I just told you a moment ago. And that is, if you have a right triangle so that the short leg and long leg relationship is that of twice as much, then the measure of the hypotenuse is equivalent to radical 5 times that particular amount of the short side. So this guy right here is going to be 100 times the square root of 5. Okay, that is a 5. Now, if that really bothers you, it honestly would take you probably less than 15, 20 seconds to do the Pythagorean theorem and come up with that on your own. Okay. There was a message in the chat about, do we need A in the equation? Why don't we use A in the equation? You know what? We actually did. Although it didn't show up over here because the derivative of A over 100 was just 100 times dAdt, we ended up using the idea of A when we found this negative cosecant squared of theta, right? The fact that A was 200 played a role in getting this value, okay? So let's think here. What is the cosecant? Again, isn't that the sine flipped upside down? So the sine of theta would be 100 divided by the hypotenuse. If you flip that backwards, the hypotenuse divided by 100 would be radical 5. We square that, we get 5, and we put a negative in front of it, we would get negative 5. Hopefully that makes a little bit of sense. And then when we divide by negative 5, your d theta dt here is going to be negative 3 over 500. Oh my gosh, that's a 3. There we go. I could probably write with my toes better on my other surface. All right, think about this. What is the label? What is the label? It's the rate of change of an angle. So that's easy, really. Anytime that you find the rate of change of an angle, you're always dealing with radians. Just apply the correct time to the problem, and that would be per second. Radians per second. Okay. All right. I've got quite a few requests for 26. We'll get there. We've got plenty of time, you guys, so I could run through a few of these. And then I had 15 actually on my radar from before as well, so we'll kind of move around a little bit. Let's see. Here's 26. Shadow problem. Now this will be this will be a little problematic, I guess, for those of you in period 5. Yes, period 5, we ran out of time, I think, and we did not get to the example number 10 in your notes. So my plan was for period 5. When do I see period 5? Well, on Wednesday, right, for period 5. We'll start class by finishing that example, and then we just basically do more of these questions, more of the questions that maybe you guys didn't get to see today in the Zoom session that you would still like to see. So we're all good, but I don't mind running through this real quickly. Shadow problems usually go somewhat quickly. So we're good to go. It says we have a spotlight on the ground 21 feet away from a wall. A 6-foot tall man is walking towards the wall at a rate of 2 feet per second as shown in the figure. How fast is the height of the shadow changing when the man is 6 feet from the wall? One thing about this shadow problem is it is set up a little bit differently than the one that we did in class. Plus, it has much better artwork than what I was able to give you. How fast is the height of the shadow changing when the man is 6 feet from the wall? All right, so what that means is, and I got to open my chat again because I like to kind of keep it open in case you guys have questions. You think I can hide my cam? Let me try it. Usually one cam doesn't really make a big difference. There's no point in having it because you guys know what my ugly face looks like anyway. So I am going to turn myself off. Let me see if this makes a difference, but it usually doesn't. I do this for students all around the country, and I'm kind of required for the businesses that I do to have the cam on, which I don't know why they think it makes a difference, but it usually doesn't fix the lag, at least with my internet at home. So how fast is the height of the shadow changing? So I'm going to call the shadow S, right? Typically, we've been doing that before, so I can call that S. The height of the man is going to be 6, okay? And we know that this man is walking toward the wall. Man is walking towards the wall. So that means that there's a distance that's sort of changing. Now, that's where it gets kind of tricky. How do you want to label this? You seemingly have like a distance over here, and maybe this is even a separate distance, or you could put the two things together and even call that yet a third distance. And I want you to know that there's a variety of ways that you can probably set this up. I'm not going to say that this way that I'm going to show you is the best way. It's just the way that occurred to me initially. If any of you think that your method was a little bit better, if we have a little bit of time, I wouldn't mind unmuting you if you want to kind of speak up. But what I thought to do was this. I thought, let's let this be X. That way, when I see this walking towards the wall at a rate of 2, I can feel pretty confident in knowing that that means that the rate of change, again, I'm going to write slow here, that the rate of change of X with respect to T would be a positive 2. Now, even though he's walking toward the wall, the word toward might imply that I should have a negative. That would be the case if maybe you were defining this distance and maybe you let this be X. Then I would say that dx dt being negative 2 would be correct. All right. It all kind of depends on whether the distance that you're focusing back on is getting bigger or smaller. Okay. Now, it says that in part A, we're going to do this or find this when the man's 6 feet from the wall. So I guess that could be part of my find. And we're finding the rate of change of the height of the shadow, but we're going to do it now when the D value is 6. So I'm just going to call this D. I could have called it anything, you guys. All right. I pretty much think that this is the only things that we need for the find and given for the way that I've chosen to set it up. As far as what our equation is going to be, well, as with any shadow problem, especially for those of you who experienced this in period 2 and 6 already, we're using similar triangles, and that's not going to change. Okay, so if this bothers you guys that are in period 5, we're going to have a much more detailed explanation about this in class tomorrow. But in a nutshell, you've got one very big triangle right here that I'm going to see if I can kind of capture. And yeah, okay, that sort of kind of worked. Let me put that over here. And in that particular triangle, I know that this side is moving around on me. Thanks. We know that this side is S. And this side, that's the one that you're going to have to think about, would be D plus X. D plus X, right? And then over here, we would have a smaller triangle, maybe something like this, that I can extract from the picture. And then I can call this side 6, and I will call this side X. At which point now I can set up a variety of similar triangle proportions, at least 3 of which that seem kind of common. Let's go with, whoops, sorry guys. Let's go with this one. Let's go with the big vertical side over the big horizontal side. How about that? We're dealing with the big triangle first. Now we're going to stick to the vertical side of the small over the horizontal side of the small. If we cross multiply, S times X equals 6D plus 6X. Okay? Now, as we kind of talk about this problem, notice that I was in no hurry to plug in some value for D and X. Yeah, I know that D is going to be 6, but I can't plug 6 in for D until I take a derivative, because that would sort of mean that this guy's not walking, right? D has to change, X has to change, S has to change. It's a little scary. We got a lot more variables going on in this problem, but we'll kind of wait and we'll see what happens. I'm going to go ahead and take its derivative the way that it's written, right? I think we're okay to do that. It's just that S times X, well, can we avoid having to use a product rule here? Trying to read through the problem here to make sure that spotlight on the ground, 21 feet from the wall. Okay, so if we look at this, thing and we're thinking, oh my gosh, we have a really complicated side here. I don't want to deal with this. I don't want to take the derivative of S times X. Well, guess what? We don't have to, because for the purpose of building this similar triangle relationship, why couldn't we use 21 for that, right? In the overall big picture, D plus X is going to be 21. However, for this smaller picture, we didn't know that. So that does change things a little bit. If we let this guy be our 21, then our right side of our equation is going to become just a little bit easier, right? S times X is going to be, what is that, 126? Right? I know this S kind of looks like a 5, but we have to interpret it as an S. And then you can do a lot of different things with this. If you absolutely despised using the quotient rule or the product rule, you could divide S or X over, or you could just leave it the way it is. And I think that's what I'm going to do. But you guys, the thing is, a lot of times you're going to be solving these problems and you're going to come against this brick wall that I just described. Sometimes you're going to have too many variables. We have to understand that this is single variable calculus. You can't be solving problems with all of these amazing number of variables. So that would kind of prompt you to look back at the problem. And to be honest, I never once used this 21, and I should have paid a lot more closer attention to that. All right. Now, if we take this derivative, S prime or S times X, we would get ds dt, I guess, times X plus S times dx dt, right? And all that would equal 0. All that would equal 0. Let's make sure. Okay, so ds dt, let's see, let me move all these windows around that are covering everything up. That's what I'm trying to find. So if I'm going to do that specifically when the man is 6 feet from the wall, and I heard somebody like 18 chats ago say, oh no, Ahmed said just a couple of chats ago that let's use 15 for X. The only thing I'm going to change about that, I'm going to use 15 for D, the way that I've set my problem up, right? Oh, I'm sorry, no. Let me take that back. The man is 6 feet from the wall. I thought that said 6 feet from the light. So the D is actually going to be 6. And that's what I said here. I should have seen that. So that would mean that my X is 15. So Ahmed, I apologize. You are right, brother. So X is going to be 15. So if I've got a 15 here multiplied by ds dt, add to that, what's S? Did we ever talk about what S was? Did we ever? Oh my God, we never even mentioned S at all, did we? Ruh-roh. That's kind of interesting. How do we find S?
Dun, dun, dun.
Yeah, there you go. That's right. So what we're going to do to find S, and we're going to mute Sean, we are going to go ahead and use the similar triangle relationship, right? We're going to have to do that. We don't have any choices but to say, okay, we've got a situation now where this is S is to 21, maybe we write it like that, as the 6 is to, well, X is 15, right? So you can set up a similar triangle relationship, however you want to do it. S over 21 works for me, equals 6 over 15. Oh my gosh, does anybody have a calculator? This is tricky. 15S equals 126. So that means that S has to be something. I don't know, something. Anybody in the chat have that? I can get my calculator out if you want me to. Okay, chat's got a little bit of a lag, so you guys might be typing stuff in and I'm not seeing it, but I'm going to type it in really quickly if the calculator will allow me to. And geez, what am I trying to look for? I'm trying to look for 126 divided by 15. And you end up getting 8.4 out of that. 8.4 or some kind of a fractional equivalent. We'll see how that decimal behaves here in a second. So this is 8.4, and the dx dt is going to be 2 times 2, and then set that equal to 0. So basically, if you guys take 16.8, yep, that's what that is, 16.8, subtract it over and divide by 15, you're going to be looking at a correct answer. That would be a correct answer. Got a couple of people that have kind of joined us late, so I'm just double checking, making sure that cameras are off. Yep.
I just noticed that I'm not muted. I'm just going to.
Yeah, I think what I'm going to do is I'm going to try to mute everyone because I think it does help a little bit with bandwidth, and it does kind of make things a little bit less laggy. Plus, we don't get like a lot of stray sounds. But at any point, if somebody does have a question, you can just kind of say in the chat, hey, I want to say something. Or there is a feature where I think you can click a button to raise your hand, and that would work halfway decent as well. Sometimes, though, I have a hard time. I have to double check and keep looking at the chat to see who's got a hand in the air and so forth. Did you guys say 15 or 18, or was it both? I heard 15. I got a lot of, I tell you what, let's look at both of them. We've got some time. Guys, if we go over about 5 minutes, I'm okay with that. I know if you have to leave, that's okay. I just have to be on my way to a meeting by about 10 or 5 till. And then what I can do is I can try to take this video with hopefully that's being recorded right now, and then I can get it uploaded while I'm in my meeting. All right. A lot of times with related rates, you guys, you just need like exposure, right? You just got to see problems being worked out one after another, and I get it. So, all right. Look at it, 15, which that's a cylindrical tank. Good thing about 15 is I think we can answer this one quickly. And I think it's a good question. I'm glad that you guys brought it up because we did not have a cylindrical problem in the notes. And there's a reason for it. And I think you're going to see that reason. So how fast does the water level drop when a cylindrical tank of radius 6 is drained at a rate of 3 feet cubed per minute? I think a lot of you might look at this and interpret the fact that there's so few numbers given that maybe it's a more challenging problem. But when in fact, when you have cylinders, things really couldn't be much easier. Because we have our cylinder and it's full of some amount of water, and we have the other stuff kind of floating around in the water, and then it's being maybe it's drained from the bottom, so water is kind of coming out. So obviously cylinders have the feature about them that talks about their height, or the height of the water in this case. But then we also have to worry about the radius. The radius is a very important measure in the cylinder. But the thing is, the water's radius is not going to change no matter what the height is. The water could be all the way to the top, or the water could be almost to the point where the thing is completely dry, as long as the whole bottom is at least still filled with some little infinitesimal thin layer of water. The radius would still be the same, and that radius is 6. So what that means, if you're okay with this, I'm going to jump right to the equation. The normal equation for the volume of a cylinder is pi r squared h. I'm going to go ahead and write it like that. That's what we would normally use, which is kind of a bummer because it's got two variables, r and h. That means we use the product rule. But since the radius is 6 all the time, we're going to use 6 for that radius. So that has just produced a much easier formula, 36 pi h. Okay, so when you take the derivative dv dt, you would of course get 36 pi dh dt. 36 pi dh dt, and then all that you have to do is plug in this for the dv dt. How fast does the water level drop is going to be your dh dt. Be really careful because I believe this is -3, right? Because the surface or the amount of water is, and that is a 3. Thanks very much for that. That is a -3. So it's not too bad of a problem because of the variable usage there. Okay. I'm kind of trying to look back and keep up with the chat, and I apologize so if I'm missing anything. And by the way, I know that I made a big point about, problems that we do in the Zoom. I didn't want to like redo it in class because I thought it was unfair to you guys because of the fact that, you're the ones that kind of sat through this, or the people that may decide to watch it, tape delayed or whatever. But if you have a question that sort of clarifies something that we did, I don't have any problem doing that. What I will do is I'll just throw the solution under the lamp already written out so that we can just really quickly kind of point to whatever kind of issue that you may have had. That way we can save some time. Okay, we are moving on to number 18. Hey, good buddy. 2 truck convoys leave 2 separate depots at the same time. Convoy A travels east at 40 miles per hour. Convoy B travels south at 30 miles per hour. How fast is the distance between the convoys changing? What? 6 minutes later? Boy, this problem was going pretty well for us, wasn't it? It seemed to be like a Pythagorean theorem type question until all of a sudden part A came in with 6 minutes later. So we'll deal with that in a second. Now we do need to decide which truck is which, and this is really up to you, but it said that convoy A travels east, so I would call this truck a truck. Hey, it's a truck, which means I'm going to make this distance little a. That seems like it makes sense to me. And then this is the B truck. It's a B truck. So I'm going to call this entire distance B. And I don't want you to be confused by the fact that B looks like it lies between, like, say, this piece of the Y, this position on the y-axis down to here. This B is the whole side. This A is this whole side between the truck and the intersection, or whatever you want to call that. All right. So we are going to then start listing out our find and all that valuable information. So what is it that we're given in this problem? Okay, that's a good question. What is it that we're given in this problem? We're given that truck A, or DADT, is moving at a rate of 40. Let's double check. Would that be a positive 40 or a negative 40? You don't have to put it in the chat. Think about it for a second. The answer is indeed positive. I wrote it correctly because A is getting bigger. What do you guys think about dBdt though? Is it positive or negative? Since this distance is getting smaller, you're going to put negative 30 right there. So perfect, good, good. We are trying to find the rate that the distance between the convoys is changing. Now I know that in this problem you see the two dashed lines, or almost looks like a dashed line and a dotted line maybe. And I have had many students tell me that that just confused them even more. And I couldn't help but agree with you. I think it does confuse you. Basically, think about one line existing between the two trucks, and that's the C. All right, it doesn't matter if you label one of these lines as the C or put a new line. I'm reluctant to put a third line in there because that just seems like it's going to make it even more confusing. So C is just the hypotenuse. And a lot of times that is the only thing that I've ever had to tell students, and they're like, oh, well, that's dumb. The picture's drawn bad. I won't disagree with you. All right. So finding dCdt. And we're going to do that specifically when 6 minutes later. I'm still a little bit kind of like concerned about that. What does that mean, 6 minutes later? Well, we'll hold on to that. You know, I can put that in here when, I don't even know what to label it, guys. When it's 6 minutes later, I guess, when it's 6 minutes later, but I hate that because I use the word it, so I owe $1 to the jar, right? So, yeah, that's going to be tricky. Equation. Well, the equation for this problem is going to be the Pythagorean theorem. I'm pretty sure that you are all in agreement on that. Okay. One thing I will say is that if you guys are working through a free response question, and if you lock into the right equation, which really isn't that hard to do for the kinds of problems that you're going to be tested on, it's not too difficult to pick up a couple of points pretty easy after that. I know that some of the problems are a lot more challenging, like the ones that you get towards the end of this assignment, and I'm actually really glad that you guys didn't ask a lot about those in the chat today. I don't mind doing those, talking about those in class, but the last few problems in the homework are very difficult, and you are not going to be inundated with problems like that on the test. You're not going to see problems remotely that challenging on the AP exam. The AP exam would probably consist of the easiest 5 questions on this worksheet out of the 30. All right. So okay. So we're going to go ahead and take the derivative here. So we end up with 2a times dA dt plus 2b times dB dt equals 2c dC dt. Now, for the first time, I think that we've done a problem together, we have a Pythagorean theorem question where A, B, and C are all going to be constant, not going to be constants. They're all going to truly be variables. So that means we got to have a lot of information. Well, we do. I mean, we already have dA dt and dB dt. What more could we ask for? That's pretty good. So we're going to go ahead and go with that, but I'm going to go ahead and get rid of my 2's because they don't mean anything, right? We have a 2 on each side that we could sort of factor out and divide away. So the question now is, what is this value of A? And consequently, what's the B and what's the C? All right. So what we're going to do here is say to ourselves, what does the 6 minutes later really mean? Okay. And if we go back to this truck A and we think, truck A, you have been traveling for 6 minutes since you've left this depot. And if truck A is going 40 miles per hour, then we know that distance equals rate times time. The distance that he traveled is what we're trying to find, because that's really this A value, even though it's called D in the distance formula. The rate, 40 miles per hour, is not going to jive real well with the minutes time of 6 minutes, right? So you need to convert 6 minutes into hours, which is just a matter of multiplying it by what? That would be 1 hour over hour, 1 hour. That's an HR up there, everyone. Over 60 minutes, which is 1/10. So T is going to be 1/10. And that makes this work out really nicely because you get 4. The distance would be 4 miles. 4 miles is how far he would have traveled during that 6 minutes. So I'm going to see if I can just kind of put this whole equation up here. I'll change colors here if that helps. So my A is 4, my dAdt is 4t, and then I've got to do something very similar for B, right? We've got this B truck who it has been on the road for, again, 6 minutes, but B is a little bit of a slowpoke. He's only going 30 miles per hour. So let's think about how far did B travel? Well, he would have traveled distance equals rate times time. So he would have traveled at his rate of 30 miles per hour, going 1/10 of an hour, right? Because that's what 6 minutes means. He's only gone 3. Now, here's the part that's tricky, and I think a lot of you are on top of this, and kudos to you. B is not 3. Do you see why? This whole distance is 20. B would have to be 20 minus the 3 that he's already traveled. So you're going to put 17 here for B. And then you'll multiply that by dBdt, which, whoops, not 30, but negative 30, right? We already established that a moment ago. Okay. Now, if you look at this special right triangle, not something special about it, but you have a triangle that has sides of 17 and 4. Okay? Call me the eternal pessimist, but I don't really know if there's a really nice Pythagorean triple for that. So you're probably going to have a decimal value for your C. C will be a decimal. Just use your calculator, and that's what's going to go right here, that decimal for C, multiplied by dCdt, and solve for this. Okay? I have no problem whatsoever giving you the answer to this problem if you want to know it. How fast is the distance between the convoys changing? And if this is not what you guys agree with, let me know. But I'm getting about, when you truncate it, it's about 20 miles per hour. I got like 20.00 something. So that's what it would be if you want to convert it to a decimal. It probably ought to be negative because it's going to be negative. You can kind of tell it's going to be negative because this guy is much, much bigger than this guy. But they should be negative because the trucks actually will be getting closer together. All right, maybe a little bit hard to see that from the picture, but indeed that is what is happening. So again, I'm going to look through the chat to see if there's anything going on. Can I repeat? Gosh, which part? I haven't been paying attention to the chat, so you guys, that message could have been like a long. Oh, the answer. Oh, the answer. Negative 20 miles per hour. Hey, if you want the exact answer, if you did the Pythagorean theorem and kept this thing like in a radical form, here's the exact answer. It's negative 350 over the square root of 305 is what it turns out to be exactly, and that would be in miles per hour. But I kind of thought converting it to a decimal makes the problem a little bit more understandable. Because I'm like, what is that? That's crazy. So. All right, well, guys, it's been fun. I hope that this was helpful. I don't think that this is by far the best medium because it's not nearly as interactive as I like it to be. But you guys were amazing. You did a good job in the chat. I need to work on some of the bugs and glitches with this. You'd think that doing this at school, I would have better internet. You know better than that, right? Some days at home, I get really nice responsiveness from my computer when I'm doing this with my other entities. And sometimes it's really sluggish from there. But I'd like to kind of start doing like a weekly office hour, like where every certain night I'll be on for an hour. You can tune in if you want, and we can just talk about things that week that you're having trouble with. So that's one of the goals that I have, and it would by all means be optional. You would never be obligated to do it. So, all right, well, guys, with that, I am going to.
Hey, Mr. Record.
Yeah, Sean, what's up?
Okay. So the question says 2 truck convoys.
Yeah.
And it depends. And
Uh-oh.
immediately came to my mind
Sean, I can't hear you. It's breaking up a little bit. You went like all robot on me. I didn't hear your question, bud.
This piece of bad comedy came.
Oh,
Oh, I was just.
that's loosely relevant
Okay,
to the
so
problem.
the question talks about two truck convoys. In Japan, Optimus Prime was known as Convoy, and that audio I just played was what I immediately thought about.
I was wondering what that audio was. I mean, all I heard was Optimus Prime over and over again, and I knew that was you, Sean. I knew that was you.
Something strange has happened. There
There
are
you go.
now two Optimus Primes.
That's right. That's right. All right. Hey, guys, I'm going to go ahead and sign off and go to my meeting. I hope that this was somewhat productive. I really do want you guys to know that you can get this. Related rates are always really kind of frustrating. I know that. I promise you that this test doesn't have to be, and it probably won't be the hardest calc test that you've ever taken. Just keep looking at it, challenge yourself with the tougher problems, and you guys are going to be fine. You really are, because I really believe if you can do the tough problems, you can do those middle of the road ones. And I even have a really special surprise for you guys next week after we take the test. Probably I'll give this to you. Yeah, it'll be Monday. Next Monday, I'll have this fun little surprise for you. So I'm going to sign off. I'm going to try to get this thing uploaded, and I guess I will see you all tomorrow in class, right? A-Day. Yay, A-Day. All right.
Yeah, it's an 8A.
All right. We'll see you guys. Take care.
Okay.